This is Dr. Indradeep Kumar, Assistant Professor at IARE, Hyderabad. So in this video, we will see about the direct stress distribution. So our lecture topic will be direct stress distribution. So first, consider a length of beam that is subjected to a pure sagging bending moment. So there are two types of bending moment. One is sagging, the other one is hogging. So if sagging is there, say here, suppose any beam is there from here to here, and this will bend like this, then this is called as the sagging. And if the same beam is bending like this, means upward side, then it is called as hogging. So what we will see here, we will see this condition, that as sagging case, not for the hogging, because when we will apply the load, right, like here, then it will bend like this, it won't go, means we have to apply the load from down to up, then only the hogging condition will be there. But generally what we are doing, we are applying load downward. So we will see the sagging case only. Okay, sagging bending moment M applied in a vertical plane. So just see, that's why it's applied in a vertical plane. The beam cross section has a vertical axis of symmetry. The beam cross section should have what? A vertical axis of symmetry. Means what? Whatever the beam is there, right, along the vertical axis, it should be symmetrical about both the axes. Okay, the bending moment causes the length of beam to bend in a manner similar to shown in figure A. So just see a first figure. So this is like here, this is any beam is there. This symbol shows that of infinite length. There is no fixed length, right? In that, what happened here? Just we have taken some small cross section of this size. What is the length of that one? Here, this is not showing a small, but it's a small, just exaggerated figure, so that you can identify how, okay, whatever the points are there. So just see here that length of this element is only delta Z, right? So that the neutral plane exists. So means in this case, what happened, that neutral plane exists, and that plane is here, this dotted one, that Z1, right? So this is the neutral plane, which is as yet unknown distance y1 and y2 from the top and bottom of the beam respectively. So just see here, from this you can see from the top of this, it's a y at a distance y1, and from the bottom at a distance y2, this neutral axis is there. So from this cross section side we are seeing, so this is the cross section of this one. This from here to here, this height is y1, and from here to here, this is y2. So for this length, we will, because we don't know where is it. Once we will know the distance of y1 and y2, according to that, we can say the neutral axis is there. If y1 equals to y2, then it will be middle point of the cross section, or whatever the shape is there. So that's why it's given unknown distance y1 and y2 from the top and bottom of the beam respectively. Means from the top it is y1 and from the bottom it is y2. Coordinates of all points in the beam are referred to axis O, X, Y, Z. O is origin and X, Y, Z is the axis. That's why it's a plural, right? So in X, Y, Z coordinate, whose O is the origin, in which the origin O lies in the neutral plane of the beam. So where O is the origin, which lies in the neutral plane. The bending moment M causes the length of beam to bend about a center of curvature C as shown in figure. So just see about center of curvature C, it will bend here. So now here along this it will bend. Okay, so just see here in this one. So the center of curvature of this ones, it will bend here. That is where the same. This here, just see. So along this one, so center of curvature. Now what distance we will take? So from this is the extreme fiber. So from here to here, the radius of this will be, that this radius of curvature will be NC. For the neutral axis, this will be the R. For the upper extreme, this you can say CP or CM. So this will be the radius of curvature for the upper fiber or upper this one, and for the neutral axis it's R, and for the this one lower one is CN. So since the element is small in length and a pure moment is applied, we can take the curved shape of the beam to be circular with a radius of curvature R, because since it's on a smaller size, so then what we are taking, that as circular of radius of curvature R measured to the neutral plane. So from the neutral plane, the distance is what? That we had seen at a distance R from the neutral plane. Okay. Next, now we investigate the behavior of an elemental length del z. So now we will see about the behavior of this elemental length of this one, right? Formed by parallel section MIN. So parallel section is M, here is I, so MIN means MIN and PGQ, right? So MIN and PGQ. So here, and also the fiber ST of the cross-sectional area delta A. So cross-sectional area delta A at a distance y above the neutral plane. So just here this ST fiber at a distance of what? Y from the neutral plane. Right. Based on this only we will consider now for this ST, if this will be 0 to Y1, then that becomes MP. If it's 0 to Y2, then it becomes NQ. So by figure also you can say MP will be equals to what? ST will be equals to IG, which is also equals to NQ, and that is equals to delta Z. So just here, ST cross this the neutral plane. Clearly before bending take place. So this is the condition before bending. Once it will bend, then it will be different. So before bending, MP equals to, so this MP equals to IG equals to ST equals to NQ, which is equals to delta Z, because it's a rectangle. So all this will be same. That is delta Z. So just see here in this figure, this is the cross-sectional part, and what we have taken that ST fiber from here at a distance y. So this is our ST fiber. Okay, elemental of that ST fiber, whose cross-sectional area is delta A at a distance y from the neutral axis. The bending moment M causes the length of the beam to bend about a center of curvature, see shown in figure. So because of the bending moment, what happened? This will start bending and it will form a radius of curvature R from the neutral axis. But from the upper fiber, it will be Cm, and for the lower fiber, it will be Cn of the radius, that radius of the curvature. Above A, since the element is small in length and a pure bend moment is applied. So here only the pure moment is there, means there is no compression and all. Only we are applying the pure moment. We can take the curved shape of the beam to be circular with a radius of curvature R measured to the neutral plane. So this point already we had seen. So now what happened after applying this moment? So like this is the beam. Now what we will do? We will apply the moment. So like this it will bend. So now just see here, first from here to here length is there. Now once we will bend like this one, so this length is reducing. So just see here, like this, first length is here, this much length is there. Now once I will compress, so just see here, the length is reducing. So this length is reducing, but what about the upper, this lower one? Lower one length will get increased, means this is getting compressed and the lower beam is getting expanded. But one layer will be there that will neither get compressed nor will get elongate or experience tension. That plane is called the neutral plane. Okay, so now here the upper one from this figure, once we will bend like this, so moment is this side, right? So now this part will get, that MP will get compressed. So hence MP size will get reduced and NQ will get elongate, means expanded. This will experience tension and MP will experience compression. But IG will remains equal to IG. It will neither experience compression nor experience tension. So that only one plane will be there in any section or any body, only one will be there which will not experience any compression or elongation. Means whatever the size before bending and after bending, that remains the same, is called as the neutral plane. So if suppose neutral, what is neutral plane? The plane which before bending and apply after bending remains same is called as the neutral plane. So same case here, this IG will not get compressed or elongate. So this is our neutral plane. So now just see here, you can see this MP will get compressed and their size got reduced and NQ got elongated, but still IG, if you will measure, it remains the same, and that's why that is a neutral plane. So now what we assume, that from R, that radius of curvature from the neutral plane is R. Means now whatever we will measure from the neutral plane only. So now just see here, as upper layer experiencing the compression. Now see MP and ST. MP is smaller than ST, means MP experiences more compression than the ST. Means along this near to the neutral axis, the just adjacent to the neutral plane fiber will experience the least compression, and the farthest one will experience the most compression. Just reverse of that one, near to this one, near to the neutral plane, the nearest one will experience the least elongation and the farthest one will experience the most elongation. Means this NQ will get elongated most, and near to just this IG will experience the less tension, and this will experience, that NQ will experience most tension. Similarly, MP will experience more compression, and near to this IG will experience the less compression. So means from the neutral plane, as it's closer to the neutral plane, one is experiencing more, the other one will be less. Means when neutral plane is experiencing more compression, then tension will be less. So just now, so how see a direct, so that's why direct stress distribution is. So how stress will be distributed, that is shown here in figure B. So just see here, this is the neutral axis. Just now I explained what, near to the neutral axis, that will experience the lesser compression. So that's why here you can see the lesser force is there, that stress distribution is less. As we move up, this experiences the most compression. So that's why here at the top only the most stress is there, right? So near to the axis means compressive strength decreases towards the neutral plane. Now what happened here, near to the neutral plane, that is experiencing less tension, so less elongation, and the farthest one will experience more elongation. So here you can see the near to the neutral plane, that tension is lesser. As it's move away from the neutral axis, it experiences more tension, means more shear stress will be there. So at the, once again, so just at the neutral axis, compression, as move towards the neutral axis, the compression will be less. As move away from the, or as move towards the neutral axis, tension will be less. Okay, or in another word, as move towards the neutral axis, compression will be least, and as move away from the neutral axis, the compression will be, sorry, elongation will be most and compression will be least. So this is the distribution of shear stress, how direct shear stress will get distribution. So that's why here it's mentioned that as sigma Z1. Now, so how we will find that formula? So just here, that is the just distribution. How much amount will be there? That by this we can find. So just see, the previously parallel plane section MIN and PGQ remains plane as we have demonstrated, but are now inclined at an angle delta theta to each other. Now what we have taken here, both are at the same angle, means it's just a parallel, right? But now we are changing the angle. Okay, so that are MIN and PGQ, means MIN, this one and this one was parallel, right? So now this and this is at some certain angle delta theta to each other. The length MP is now shorter than del Z. So now definitely length MP will be what? This will be shorter. So just see, only this much length is there, right? So length will be shorter than delta Z. Okay, and ST will, okay, the length MP is now shorter than delta Z as it ST, while NQ is longer. So now the NQ will be longer. IG being the neutral plane is still length delta Z, because now the neutral plane is not only before bending moment and after bending moment, what remains same. So here it won't get affected, means neutral plane IG remains the same. Since the fiber ST has changed in length, it has suffered a strain, what? Epsilon into Z from Hooke's law. Hooke's law was, according to Hooke's law, the stress is directly proportional to the strain. So stress is sigma is directly proportional to epsilon. From now, apply the Young's modulus. So, or modulus of elasticity. So sigma will be equals to Z into epsilon. right? So this is that. Okay, suffered a strain epsilon z, which is given by, so epsilon, so this is epsilon z means along the z direction. So this epsilon, right, along the z direction. So epsilon will be what? Strain is change in length by original length. Now what is change in length? Actually it should be what? R minus y into delta theta with theta minus delta z, right? So this is the original length. Now what is the new length? That is R minus y into delta theta. So final length minus initial length by the initial length or original length, or final length minus original length by original length. So this will give what? Change in length or strain, because strain is defined as change in length by original length. So here, now epsilon naught z equals to what? R minus y into delta theta. Now from the figure you can see that delta z will be equals to R into delta theta. So just replace both the place R delta theta. Now after this what we can do? Just let's expand. First multiply and then expand this equation. So after multiplying this delta theta to both, what we will get? R delta theta minus y delta theta minus R delta theta by R delta theta. So now see this R delta theta get cancelled. What is left? Minus y delta theta by R delta theta. So now this delta theta cancel. What is left? Minus y by R. So that is epsilon z equals to minus y by R. So now we got the strain with what? At what distance we are considering. What was y? The fiber length, that fiber distance from the neutral plane, that ST distance. So at what position we are finding that divided by the radius of curvature, or the distance from the neutral axis to the center. So that much will be there. Now this depends on the value of y, because radius of curvature will remain same. So that depends on the value of y. At what fiber we are considering this. Now suppose from here to here this distance is y. So once this will be y, so y will be more, this strain will be more. So that's why at this point the strain will be more, and here near to this the strain will be less, because the value of y will be smaller. So as value of y will be bigger, right, the strain will be bigger, or the strain will be more, and y value of y will be smaller, the strain will be smaller. So now we got a strain along the z direction epsilon z equals to minus y by r. Now the negative sign in equation 16.1, that is just here, because just to refer I mentioned, because the reference point in the reference book is Maxen. So in Maxen you can see the 16.1 equation is this one. So just for reference I added the same equation what is given in the Maxen. So from here you can see that this minus sign is there. So this is according to the Maxen, this is the equation number 16.1. Right, indicates that fiber in the region where y is positive will shorten when the bending moment is negative. So when bending moment is negative is what? Y is positive, hence that becomes shortened, or you can say it's experiencing the compressive force, or it gets compressed. Then from equation of the direct stress, sigma z in the fiber ST is given by, so sigma, this is sigma z here. So sigma z equals to what? E into epsilon naught, E into epsilon z. So sigma z equals to E into epsilon z is what? Minus y by r. So this we can write sigma z equals to minus E into y by r. So that is here, sigma z equals to minus E into y by r. The direct or normal force on the cross section of the fiber ST is sigma z into dA. The cross section is what? Sigma z, sigma z. This is sigma z into delta A. That will be the normal force. Force is what? Sigma into area. So sigma z. This is z subscript. Sigma z into delta A is the force. However, since the direct stress in the beam section is due to pure bending moment, that already we considered that we are taking the pure bending moment only, not other things. So pure bending moment, what happened? The other moment of forces will be 0. So in other words, there is no axial load. So just here, that's why there is no axial load. Because of axial load, the compression will be there, but we are taking here the pure bending. So there is no axial load. The resultant normal force on the complete cross section of the beam must be 0. So the resultant force also what? It must be 0. So whatever the resultant force is there, just make it equal to 0. So from here only, that over the entire cross-sectional area, integral A is entire cross-sectional area, that sigma z into dA must be equals to 0. Where A is what? Area of the beam cross-section. So integral of over cross-section beam, sigma z into dA will be equals to 0. Substituting for sigma z in equation. Now substitute sigma z is what? Just now we got here, this minus Ey by r. So substitute here. After substituting, what we will get? So integral A sigma z is minus E into y by r into dA. That is equals to 0. So that only after substituting here. E is constant, r is constant, take out of the integral. So integral of A minus E by r out, and integral A y dA equals to 0. Now y dA is what? That moment of inertia, in which both E and R are constant for a beam of given material subjected to a given bending moment. Therefore, now these two take this side, that also becomes equal to 0. Hence, integral A y dA equals to 0. And this is what? Area moment, and which is also called as the moment of inertia. Now, consider now the elemental strip delta A in figure B. So, in figure B, that delta A strip is there. This is in fact the cross section of the fiber ST, right? That is here. The strip is above the neutral axis, so that there will be a compressive force acting on its cross section, sigma z into delta A, which is numerically equals to, just now this we find Ey by r into dA from the previous equation. As here in this figure, right, at a distance. So this will delta A experience is there. So definitely this will be sigma z into delta A. It will experience the force. Note that this force will act at all section along the length ST. So wherever ST is there, along all the length, means this will act along all the points along this all ST. At S, this force will exert a clockwise moment, which is equals to Ey by r into y dA, right? Because Ey by r into del A is force, and into y will give you the moment about the neutral axis, while at T, the force will exert an identical anti-clockwise moment about the neutral axis. So it will be same Ey by r into delta A, that is the force, into y, the same moment but in anti-clockwise direction, or you can say in opposite direction. Considering either end of ST, any side, right, we see that the moment resultant about the neutral axis of the stresses on all such fiber must be equivalent to the applied negative moment. So whatever the side you will take, right, either towards S or towards T, the overall it will be what? The resultant will be along the neutral axis of the stress on all such fiber must be equivalent to whatever the negative moment applied, that is M. Means what? M, that is equals to, M equals to minus integral A E y to that y square by r dA. So Ey, this one, Ey by r into dA is the force into y. So for first what happened? Moment is what? Moment is force into perpendicular distance. That integral of this one, right? A. So now after substituting the force value, what is that? Integral E, okay, y by r, that minus sign, into dA. So this is the force into y for moment. So now this y becomes y square. So integral A minus of this one E y square by r into dA. So this will be the moment, and that is here E y square by r dA. Now again take E by r common. So M equals to minus E by r common. Integral A y square dA. Right. So now from here ER is constant. So now here this integral A y square dA. The term integral of y square dA is known as the second moment of area. This is called that term what? Integral over entire area, that cross sectional area y square into dA is the second moment area. Means area moment. Whatever area is there, take the moment of that one. Moment of moment area. So first dA into y is the moment of area and into y is the second moment of area. Okay, of the cross section of the beam about the neutral axis and is given the symbol I. And so this is only represent which we are also saying that what this is the moment of inertia. Second moment of area is the another word. Generally we are using the moment of inertia. So that we can say I equals to integral of y square dA. Now it depends on along which axis it is. Then if along the x-axis, then we will write ixx. Along the y-axis, then iyy. Along the xy axis or along that plane, then ixy or iyx, depending upon which plane we are taking. Okay, rewriting equation, what we have, m equals to minus ei by r. So now just substitute here for this as I. So minus ei by r. Or combining with expression with 16.2 from same again. Now just m by I, take this one. From here what we will get, m by I equals to minus e by r. And from here already we got this minus e by r equals to sigma z by y. Right, because sigma z was equals to minus ey by r. So from here we can write sigma z equals sigma z by this y. So by y equals to minus e by r. So now here we got m by I equals to minus e by r, and from here we got sigma z by y equals to minus e by r. So combine all the three equations, and after combining what we will get, that m by I equals to minus e by r equals to sigma z by y. Okay, so this equation is very important. Okay, so what is sigma z? That as my by I from here. So from sigma z we will get that as, or just take these two. So this one and this one. So from here sigma z equals to my by I. So now this formula if you will remember, and after that you have to just check what are the things given and what is missing. So definitely out of just here, if you will take these two, this total 4 terms are there. Means 3 should be known. Okay, if you will take these two, means any two you can take in that. 3 should be known and 1 should be unknown, then only you can find. So what you will do, you have to check first what are the things given and what you have to find. According to you have to select. Okay, if suppose m is given, I is given, r is given, right, you can find e. But now you are using this formula, then where you will put the value of m and I? You cannot put. So whatever the value is there, according to you have to choose two things, either this or this. Any two combination you can choose to find the unknown one. So like suppose from this one and this one, sigma z if you want to find, then sigma z equals to my by I, or if you want to find m, then m will be equals to what? Sigma z into I by y. Like that you can just cross multiply and change whatever you want. According to that you can find the unknown value. So just you have to remember this formula, and then whatever the value is given, according to that you just substitute. The direct stress sigma z at any point in the cross section of a beam is therefore directly proportional to the distance of the point from the neutral axis, and so varies linearly to the depth as shown in figure. Right? So what happened from here, you can say sigma z is m by I into y. So this m by I is constant. So from here we can say that what? Sigma z is directly proportional to y. Means if y will be more, sigma z will be more, and that only is here that I told you. That now we will see how. So this y is less, so sigma z is less. As y increases, sigma z increases. Now, and that negative sign also it was there for the compression, so that so it goes up, and positive is here. But that depends on what? The y value. Here in this case, if you will come down, y is less, so less stress. Y is more, so more stress. Means it totally depends on the position of that fiber with from the neutral axis. Clearly, for a positive bending moment, sigma z is positive, that is tensile, when y is positive, and compressive, that is negative when y is negative. Means when y is negative, that is compressive. When y is positive, that is tensile. So sigma z1, right, for compression, my by I, that is for compression, sigma z2 my2, because at second position. So just simply y replaced to y1 and y2, because in the starting itself we considered y1 from the top and y2 from the bottom, from the neutral plane. So that for tension, sigma z2 will be equals to what? My2 by I, that is tensile or tension, sigma z1, that is my by I, which is compression. Furthermore, we see from the equation that m equals to minus ei by r, that the radius, the curvature 1 by r of the beam is given by. So now from here, what we can find, 1 by r equals to m by ei. So from this one, 1 by r, or radius of curvature, equals to m by ei. This directly we can use there, or for m we can write simply what? Ei by r, and is therefore directly proportional to the applied bending moment. So radius of curvature, that 1 by r, is directly proportional to what? M, because E is constant, I of that particular beam or cross section is constant. So only the variable is M. So radius of curvature will depends on how much moment you applied. So now come to this figure. So this length means this moment, how much it will get compressed, that depends on this moment value. If this moment will be less, this will get less bent or less compression will be there. If this moment will be more, the more compression will be there. So, and according to the compression only, the size of the radius of curvature will be there. So from you can see the radius of curvature is directly proportional to the applied bending moment. So yeah, moment, okay, and inversely proportional to the product EI. What is EI? That is called as the flexural rigidity. E is Young's modulus of elasticity and I is moment of inertia. The product of these two is called as the flexural rigidity. So it's inversely proportional to what? And 1 by r is inversely proportional to 1 by ei, that is flexural rigidity. Right? Okay. So this is again this, what is that? Your reference book, T.H.G. Mixon, and that's why wherever that equation is required, I am putting the same equation so that you can refer to this book and you can get that equation, because all the equation mentioning that is not possible in this one. So from where you can just, for your reference, I am putting the same equation so that in that book you can see the same equation number and then you will understand the whole thing. So if you have any doubt regarding this, you just comment on the video or you can just contact me. I will clarify your doubt. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.